All right, today we are going to get into the the meat and the gristle of relativity, special relativity more specifically. Um, but first, your warm up question, and this ties into what I mentioned for yesterday. What is the speed of gravity? It's not instantaneous. There is a speed to gravity, and what is it? The speed of gravity is the speed of light. Um, which in general, again, I said this earlier for yesterday. Let's see, where should I say? Yeah, the speed of light should be called the speed of bosons because all bosons move at this speed. So this speed again, photons, gluons, well, gravitons. So in other words, all of these forces are at the speed of light. So the speed of light, which is for a second. Okay, now you may want to be super technical and say that hey, the speed of light's not exactly that, which like, okay, fine, it's not exactly. What is it? Let me look it up. Speed of light. It's like 298 million or something. I don't know. Why is Wikipedia not loading? What did you do? See, look what happened. um. Okay. Yeah. See, it's like. Okay. All right. Yeah. See, here it is. It's 200. This is your technical speed of light. Uh, speed of light is more precisely this number. However, you can see why we just use 300 million because it's real dang close to that. Um, Now you could actually argue that for what we're about to do, you could get into situations where you actually do care about the precision of this number, but we're just going to use 300 million because it's just so much easier. So we're not going to worry about that. Okay, so I mentioned before that with this whole relativistic stuff that we mentioned, talked about how you could have actually two events that where you get into a situation where depending on what your reference frame is, you actually see different things happening. That gets compounded and gets weird as you start moving close to the speed of light. And this is very weird. So it's hard to really kind of get like a conceptual understanding as to why. The short answer is that it took until Einstein to figure it out. So it's weird and confusing. But basically, the premise was, and this is actually kind of solved for when people were talking about light in general, because again, talking about speeds being relative. So the question is, well, this speed here, this speed of light, what is this speed relative to, right? Because for example, like wave, like a water wave, the speed of that wave would be the speed of the wave going through the water compared to like the water itself without the wave, right? So that's the situation here. But then the question is, well, then what are we measuring light compared to, right? And we didn't really have an answer for that. And there's a whole lot of theories about like, oh, there's this stuff in the universe that just is everywhere called the ether, and like light is the speed relative to that. But like we had no evidence that that existed, and then even some experiments that proposed to like determine the ether was there, like didn't do that. So there was this is like late 1800s kind of figuring this out, and like nobody really knew what they were doing. And then Einstein was like, okay, let's just assume the speed of light is this number, and it's not that it's relative to whatever. It's just that is what it is. If you assume that, then you end up getting some very weird things happening. And so let me sort of right into this. So when objects start moving close to the speed of light, things get weird. I know that's a very scientific explanation of this, but you'll see. The amount of weirdness uh, can be calculated with a value known as the Lorentz factor. Okay. I want to get that off the page. Okay. So the Lorentz factor is basically a way of saying, okay, depending on how fast you're going, things are going to get weird. And the amount of weirdness is this Lorentz factor number. So here's how you solve for this. And again, this is only dependent on the speed that you are going compared to another thing. So really the Lorentz factor is basically, it's the weirdness factor between two different things, right? So for example, if I'm walking, 2 meters per second, then my Lorentz factor would be based on that 2 meters per second speed of me compared to the Earth. So in that case, technically I should say it's my Lorentz factor compared to the Earth. For example, you could also have my Lorentz factor compared to Andromeda Galaxy, or the Earth's Lorentz factor compared to the Sun, right? You could do all kinds of things with that. So that's how this works. So how do you calculate this? Well, first of all, the number itself is denoted as, I have to find the right shortcut for it. Nope, wait. Nope, wait. That's theta. Okay, so it's 945? Nope, 947. Yeah, that's it. Okay. So that's a lowercase gamma. Okay, it's not a y, it's a lowercase gamma. Yeah, so that's what the Lorentz factor is, a lowercase gamma. So the Lorentz factor is solved with this equation here. Okay, so c equals speed of light, and v equals your speed. Okay, and this will get your Lorentz factor. So let's show that down a little bit more because there's stuff here. Okay, so again, the only number that really changes is this speed, right? Because speed of light is constant, everything else is constant. So let's get an actual example of what this looks like. For example, again, the Earth. The Earth moves at about 30,000 meters per second around the Sun. Find the Lorentz factor of the Earth relative to the Sun. Okay, so you would have, well, I have 1 over the square root of 1 minus, so this is now is my speed, it's going to be 30,000 squared divided by 300 million squared. And close that parentheses. There, yeah. So, I'm just going to put this in a scientific notation just to make this easier to deal with. So, 30,000 squared, this is 3 times 10 to the 4. And this is 3 times 10 to the 8. So if we square this, we get 1 over, whoops. What the heck is that? Wrong thing. Divided by 1 minus, okay, so this squared you end up getting, this is 9 times 10 to the 8 divided by 9 times 10 to the 16. Okay, so the 9s cancel, 10 to the 8 divided by 10 to the 16 is just 10 to the minus 8. So you get the minus 8, which means 1 minus that is going to be 0. Make sure I get this right. 9999999, I think. Hold on. Let me double check that's the right number of 9s. Okay, 10 to the minus 8, and then minus 1, and then I know it's negative, but wait, there's the, okay, so that's 4 9s. Yeah, so there's that's your number, but that's in a square root, so you got to square root this, and oh boy. I'll just round this up to 5. Okay, so we have That's 5. And then you do 1 over it, and you get that the Lorentz factor of the Earth compared to the Sun is basically this. That's 8 zeros between the 1 and the 5. So you will notice that that number is very close to 1. Now, if your speed is 0, so if this was 0, then what do you get? Well, then you just get this whole thing just becomes 0. So then 1 minus 0 is just 1. And then you get the square root of 1, which is 1. And then 1 over that, which is just 1 over 1, which is 1. So at v equals 0, your Lorentz factor is just 1. Basically saying, hey, how is everything, how are your values? Well, it's just normal. It's 1, right? So that's showing that you're never going to have a Lorentz factor that's less than 1. So let's see. Let's actually have like a little chart here. So let's have whatever your velocity is, and then whatever your Lorentz factor is. So if your v is 0, then your Lorentz factor is just 1. Now, 30,000 meters per second is, pretty fast, but you can see that this is very close to 1. So even with the Earth going around the Sun, it's not like things are going to get that weird, right? You're not in the territory of like weird speeds at this point. So let's actually jump to 1% the speed of light. Okay, so that would be 0.01 c. So if you have your speed compared to the speed of light, this actually makes things easier because, for example, then you have in the square root part, you have 0.01 c squared divided by c squared. The c squareds just cancel, and you're just left with... Well, okay, hold on. All of that is squared. So this turns into 0.0001 c squared divided by c squared, right? So but then the c's cancel, and you're just left with whatever this number is in front of the c. You're left with that squared. So that's kind of a shortcut to figure this out. So 0.01 squared. Then we have 1 minus this. And then we have the square root of this. And then we have 1 over that. So that's 4 zeros and then a 5. Okay, so again, you can still see 1% the speed of light. That's 3 million meters per second. You still have barely a difference here. You have 0.0005 of a difference. 10% the speed of light. That's 0.1 c. What do you get? Well, again, 10%. So we are going to square that. So 0.1 squared. And then 1 minus that. And then square root it. And then do 1 over that. And you get 1.005. Yeah, and it's a little bit more than 1, but it's still pretty close to 1. We're 10% the speed of light here. Let's jump all the way to 50% the speed of light. Half the speed of light. Okay, at this point, your number is probably going to be, pretty big, right? So at this point, well, again, we do 50% squared. So 0.5 squared. Then 1 minus that. Then square root of that. And then 1 over that. Okay, 1.1547. So even at 50% the speed of light, we're still at 1.1. Okay, you know what? Let's jump all the way to 90% the speed of light. So 0.9 squared. 1 minus that. Square root of that. And then reverse of that. Okay, we're over 2. 2.294. Okay, so it's not bound between 1 and 2. It can go greater than 2. Let's now do 99% the speed of light. Okay, so 0.99. You square it. Do 1 minus that. Then you square root it. And then you inverse it. 7.0888. Okay, so now the number is suddenly jumped to 7. But again, we're at 99% of the speed of light. Let's do 0.999c. Okay, just adding another 9 onto this. 999 squared square root inverse 22.366. And I'll do one more. 0.9999c squared 1. Here the negative. Okay, then square root inverse 70.712. Now, what if we are at the speed of light? What if we are at c? 1c. What is this? What is our answer? Well, what do we have? We have the speed of light squared divided by the speed of light squared. That's just 1. 1 minus 1 is 0. Square root of 0 is 0. 1 over 0 is infinity. So this ends up getting... Is this infinity? Nope, that's not infinity. Which one's infinity? No, hold on. I'm determined to find where infinity is. Oh, there it is. Okay, that was close. It was 236. Okay. These are all alt key codes, by the way. Okay, so it's infinity. So the range of this is 1 to infinity, except it is very close to 1 for a very long time, okay? From any speed up till, somewhere between 50 and 90% the speed of light, it's 1. And then, but it can get all the way up to infinity, okay? For example, let's do something extreme here. Let's just do that, and then squared 223,000. All right, so this can get very, very extreme. If you were to graph this, you would see it's like flat, 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 flat. Whoop! It just goes up like there. So this graph, this Lorentz factor is very close to 1 for a very long time. So then the question is, okay, what does this mean? So I said the Lorentz factor is basically a way of mathematically describing the weirdness from relativity. So how does that come about? What this means is that just like how I said that from your different reference points, you observe different things. Again, the whole person on the train of the lightning bolt and stuff. You observe different things. That's what happens here. Basically, if there's something that's moving versus something that's not moving, the Lorentz factor tells you the difference in values between what the two things observe. So let me explain how this works. Again, this is very weird to explain conceptually. So the Lorentz factor tells you how different certain measurements are depending on the speed of your reference frame. Okay, so, and I'm going to just kind of, and again, this is very weird to explain, so let me just kind of write this in for first. Let's see what we have. We want t times Lorentz factor. L, we want it to be divided, and what's the last? Oh, m. M, we want to be also multiplied. Okay, so what the heck is this? What does all this mean? So, T, L, and M are the time, length, and mass measurements that are measured when not, hold on, how do I phrase this? Measured within the reference frame of the object you're measuring. Okay. T prime, L prime, and M prime, and this is nothing to do with calculus, by the way, in terms of primes. That's how it's worded. Are the time, length, and mass measurements that are measured outside the reference frame of the object here's what this all means, because this is like a lot of just words and hard to put together. Let's say you were on. Okay. This is very weird, very hard to explain. So let me do my best here. Let's say you're standing on the ground, okay, and you see a spaceship fly past you at 10% the speed of light. Okay, ignoring the fact that, like, you are how you could actually see that happening and that kind of stuff. And let's go even further. Say somehow while it's flying past you at 10% the speed of light, you can measure this spaceship's mass, length, and its time. Okay, so let's say a spaceship carrying. Okay, you know what? Okay, carrying a person is moving at 10% the speed of light for 1 year. The person's mass is, I'm just going to make the numbers easy, 100 kilograms, and his length is 0.1 meters. When I mean length, by the way, I mean, like, it's in the direction of the thing that's moving. So, for example, if he's in the spaceship, and let's say he's standing just facing toward the front of the spaceship, then the length would be like the distance from the front of them to the back of them. Okay, so that's why I said 0.1 meter. It's a bit short, but not whatever. I'm making it, especially for 100 kilograms, but I'm just making the numbers easy. So, it's the direction that, like, you're actually moving towards. So, for example, if he was, like, lying down, right, so his head was, like, towards the front of the ship and his feet were towards the back of the ship, then that's the length you're talking about. Then, you know what I mean? So it's the direction that is actually with the direction you're moving. So that's what I mean. So the person in the ship, that's what they're measuring, okay? So if the person who's in the ship, he's standing on a scale, it reads 100 kilograms, you can measure his, length, in that case, front to back, is 1/10 of a meter, and he's on the ship for a year, okay? So that's what he's doing. Another person is outside of the ship watching it go by. Let's see this new sentence. What numbers do they measure for the person's mass, length, and time? Okay, so the Lorentz factor from this, the first thing to do in any sort of relativity question is just find the Lorentz factor, and that should be pretty easy if you're given this. If you have the speed. If you don't have the speed, well, then you have to figure that out somehow. So 10% the speed of light, we actually just have that up here. So 10% is 0.005. Or 1.005. So is 1.005. There's no units for this, by the way, so don't worry about that. So what this means now is, okay, so we have Lorentz factor, and let's see, we have the time is multiplied, the mass is multiplied, and the length is divided. So T prime, let's go reverse order. So M prime equals M times the Lorentz factor. Now, you have to be careful. Which M are you given? Which one are you solving for? So in this case, this M that doesn't, the one that does not have the prime thing on it, these variables are measured by the person who's in the moving thing, or the thing that is moving. So this would be the mass measured while they're moving. And this person is moving. The person's mass is 100 kilograms, and he is moving in the ship, okay? So this person's speed compared to the moving object, which is the ship, is 0, because he's standing just in the ship. So in this case, yes, we do have M, and we're solving for M prime. So in this example, then, M is 100 kilograms times 0.5, so we get 100.5 kilograms. So what this means is that someone outside of the ship, watching the ship go by, if they could somehow measure the person's mass inside of the ship, they would not measure 100 kilograms, they would measure 100.5 kilograms. They would measure an extra half of a kilogram. L prime is a division. And again, this L is the number that's measured from inside of the ship, which is what it is. So we have 0.1 divided by 1.005. which gives us okay, basically 0.0995. Okay. So instead of 10 centimeters, this is 9.95 centimeters. Okay, so what this means is that, again, the person inside of the ship, he's looking at himself and he's like, okay, my length is 10 centimeters. But someone outside of the ship, if they could see the person's length and they measured it, they would see, hey, that person is not 10 centimeters long, which sounds weird to say, but okay. They're 9.95 centimeters long. They are actually shorter. They're squished in a little bit compared to what the other person saw. And then time is also a multiply, and so that's 1 year, so it's just 1 times 1.005, which means 5 years. So here's the really trippy thing. This means that the person inside of the ship, he's been in that ship for 1 year. But for anyone outside of the ship, they will say, hey, you were not in that ship for 1 year. You were in that ship for 1.005 years, which, how many extra days is that, actually? I'll do 365. Almost a bit more than 1 extra day. Okay. So, like, almost 2 extra days. So, what this mean? And so, this is the stuff that gets really crazy. Then gets back to the question I said yesterday, where it was like, who was correct, right? Did the lightning strikes hit at the same time, or was one after the other? And I said both. Same thing here. What is the person's mass? Is it 100 or is it 100.5? They're both right. They're right from their perspective. What is the length of the person? 10 centimeters or 9.95 centimeters? They're both right. And then, how long did he spend in the ship? 1 year or 1 year and 2 days? And the answer is both. He spent both the time. And so how the heck is that supposed to work? It's very strange, and there's two main things that kind of come from this. But one of those things is that the first thing is that I'm going to talk about actually is from time. So what this means is that let's say, I'm the person on the ship. I step onto the ship January 1st, okay? And I have my calendar, I have my, my clock, whatever, that's on the ship with me, and I'm traveling at 10% the speed of light, and then I check, okay, yep, now all of a sudden, it's January 1st, now the next year, 2021 or whatever, right? And I step off my ship, and I say, here I am, I have been on the ship for 1 year, and it is now January 1st, 2021. Okay, and I got in January 1st, 2020 or whatever. Someone else, though, who will greet me after I come out of the ship will say, no, it's not January 1st. It's actually January 2nd, near the end of January 2nd. January 2nd, like late in the evening or whatever. And you're both right. So in other words, what I just did is I spent a year in a ship while the rest of the world spent a year and like about 2 days. And so in other words, I time traveled in the future by like almost 2 days. So this is like actually like a legitimate thing. This is not, screwing around with semantics or whatever. No, this actually happens. And you can get some stuff that's happening that's very, very strange. For example, you could have a twin. Okay, let's say, and I know twins don't work like this, but let's say you and your twin are born at the exact same time. Obviously, that can't happen, but let's assume it does. Then, if so you're exactly both, let's say, 25 years old. Then one of them gets into a ship that's moving very fast. Let's say, closer to, let's say like 90% the speed of light. Okay, so he's moving at 90% the speed of light, and he spends 10 years on this ship moving at 90% the speed of light. Okay, so if he spends 10 years moving at 90% the speed of light, that means reality, everything outside of the ship, will have spent, 22.94 years, basically 23 years. So in other words, he got in at age 25, he steps out, he's 35 years old. But his twin, who is age 25, by the time he comes back, it will have been almost 23 years, he'll be almost 48. So biologically, one of them will have lived 10 years, the other one will have lived almost 23 years. So these twins who would have looked the same, one of them will look like a 35-year-old and will be biologically a 35-year-old. The other one will look like a 48-year-old and be biologically a 48-year-old. Okay, this is legit, straight up. I time traveled into the future. Okay, this is what this is. This is not like any kind of sleight of hand. No, it's not actually how. No, this is what happens. You literally are time traveling into the future when you do this, and also this also means, again, this is only dependent on your speed. So technically, just by walking forward, you're time traveling into the future. If granted, if your velocity is just 1, if you plug 1 into this, the Lorentz factor you get is unbelievably tiny. Let's see if this calculator can even handle it. So 1 divided by, that's 9 times 10 to the 16 is the speed of light squared. So that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You get that. So then it's minus. Okay, it is handling it so far. Square root of that. Okay, and then inverse of that. Okay, there you go. So if I'm walking at 1 meters per second, and how many seconds is that needed? I don't know. And I walk for, I don't know, let's say a whole year. I'm walking straight for a year. I'm Forrest Gump, well, he was running, but whatever. For a whole year. So that would be, let me see, minus 1 with that. Okay, so that's 4 hours times I've time traveled that many seconds into the future. Okay, so by moving at 1 meter for the whole year. So again, when we're just doing stuff on the Earth, this doesn't matter. But when you're talking about things moving, through space, then it can matter. And you get to some kind of crazy results here. And again, this is legitimate, full-on, actual time travel into the future. And you can get some just absolutely insane things. For example, let's actually look at okay, so we had the Lorentz factor here for Earth. So this here was the Lorentz factor of the Earth. So let me actually write this down. So we have, this is Lorentz factor of Earth compared to the Sun. Okay, so what this means is that, again, the Earth, now on the Earth, we've measured the mass, the radius, and the age of the Earth. We know these things. So we are standing on the Earth. Therefore, the Earth is not moving with respect to us, right? We are on it, so therefore our numbers are going to be the not prime numbers. So the mass of the Earth is 5.972 times 10 to the 24 kilograms. The length of the Earth, which would be just double the radius, I guess. Okay, so 1.2742, which is 10 to the 7, okay. And the age of the Earth is 4.54 billion years, so times 10 to the 9 years. Okay. So, we can use the Lorentz factor to solve for, what we can do is, again, this was the Lorentz factor with respect to the Sun. So in other words, these are the numbers we get while we are on the Earth. But if we were on the Sun, what would we see instead? Okay, and so we can solve for that. So m prime is going to be 5.972 times 10 up to the 24 times 1 point. That's 8 zeros, yeah. That. So 5.972 times 10 to the 24 times 1 point, 1, 2, 3, 4, 5, 6, 7, 8. That. So the Earth, you get that. So that is, oh boy, okay, that's 4 zeros. And then 2986. So that is, okay, that is 1,000, million, billion, trillion. So that is, okay, an extra 2.986 times Okay, so the sun thinks the Earth is this many extra kilograms. Okay, in terms of length, 1.2742 divided by. So now we're dividing. So 1.2742. Okay, and we get that. Boy. These numbers are not great to work at. Okay. 2.741, and then how many nines? 3 nines. Point. Okay. 493629. So this is now less. It's now slightly shorter. So we want to, let's see, subtract 1, 2, 2. Yeah, okay. So the Earth is an extra. It's 6.37 6.37 centimeters shorter, smaller, I don't know. And then time 4, 5, 6, 7, 8. 4.54 times 10 to the 9 times 1.1234567 okay, so that is a little more manageable. 5, 4, and that's 5 zeros. So it's an extra 22.7 years old. Okay, so what does this mean? This means that from us standing on the Earth, we think that the Earth has a mass of this, has a length of this, again, think diameter, and has lived for this long. The sun, separate from the Earth, watching the Earth going around it at a speed that gives it a Lorentz factor, thinks that its mass is this many extra kilograms, is 6 centimeters shorter than it actually is, and that it's lived an extra 23-ish years. So again, you can see that it's weird. It's how this works. It's weird how this all comes together, but this is accurate. This is what actually happens. And yeah, it's very weird. It's very, very weird. I don't really know what else to say about it. Now there is another thing that, so let's extend this to the full thing. So when you're moving at the speed of light, your Lorentz factor is infinity. Okay, so let's actually think about this. So at the speed of light, the Lorentz factor is, was it, 234? No, 236. Yeah, okay. So therefore, M prime. What is M prime? Okay, so M prime, if its mass is the mass times your Lorentz factor. So therefore, your mass becomes infinity. Your length, you're now dividing by the Lorentz factor, so you're dividing by infinity. Anything divided by infinity is 0. And your time is also a multiplication, so then that is infinity. Now, this is why, when people talk about, oh, you can't go faster than the speed of light, the question is why? This is why. If you were to move at the speed of light, first of all, your length would be 0. So in other words, if I'm running at the speed of light, my body will become infinitely thin, okay? Which is problematic, but, that's the least of your problems, to be honest. Your second problem, so let's see. So you would become infinitely thin. Your mass would be infinite. Meaning you would need, and again, think about energy, right? Kinetic energy, 1/2 mv squared. If your mass is infinite, your energy is infinite. So in other words, meaning you would need infinite energy to move at the speed of light. So again, that's impossible, hence why moving at the speed of light is impossible. And here's the thing, if you are a photon, or another thing that does not have mass, well then it's fine, right? Because then we're saying, oh, it's our mass is 0 times something that approaches infinity. Well, it's still going to be 0. So then it's not an issue. But if you have any mass at all, even if you're like an electron, if you're moving at the speed of light, you suddenly need an infinite amount of energy, and it doesn't work. Okay, and your time is infinite. Now, this is a weird thing. What does it mean by infinite time? So what this means is, again, that your perception of time... remember, t prime, all the prime numbers are the values that are measured outside of the moving object. So in other words, if I was moving at the speed of light, that means the world around me passes by at an infinite amount of time. So what this means, like, conceptually, is that, and this is how we think this means, is that from light's perspective, it does not experience time. Okay? So light that's emitted from the sun, it takes 8.5 minutes to get to the Earth. But from the light's own perspective, it's both at the sun and at the Earth at the exact same time. And that doesn't make any sense, like, to us, because we don't experience reality like that. But we think that's how it works. And so again, you can imagine why once we have like actual objects with mass that like this just doesn't make any sense. So this is why people say we can't go faster than the speed of light. It's because you would need an infinite amount of energy to do so. And again, if we go further, if we have a number that's greater than the speed of light, going back to this formula, so in other words, this divided by this is greater than 1, okay? Well, if that's the case, then 1 minus that is going to be a negative number, and then we have a square root of a negative number, okay? So then that doesn't work, right? So Lorentz factor being imaginary doesn't make any sense. So yeah, this is the basis behind why that moving faster than the speed of light doesn't work. Yeah. This is very weird. It's very weird conceptually. It's mathematically, the math itself is easy, right? You're literally just, you're plugging in a number into this formula, and you're getting a number, which is, it's not the easiest formula in the world, but it's pretty simple, all things considered. And then you're taking that number and just multiplying it or dividing it by some other number. Like, that's pretty easy. The difficulty is understanding conceptually what the heck this means, and what you get from that. And it's hard. I don't know really what to tell you about this. Again, it took until Einstein to figure it out, so it's not easy at all. And again, this is the simplest example of relativity. General relativity. So, okay, special relativity is what we've been talking about, and that's all talking about how fast you're moving. General relativity is when you start throwing acceleration in there, and forces in there, and other stuff like that. And then it gets, more general, and it gets into, like, tensors, which I think I mentioned before are like multi-dimensional vectors, and like matrices, and it's awful. So we're not dealing with that. But yeah, so even with this, it's still very hard to wrap your head around, and the fact that like time travel to the future is absolutely possible. You just need to have a crapload of energy and be able to move a thing very, very fast. And again, it does matter in our, not everyday lives, but in terms of our technology working the way it does. Yeah, GPS satellites actually moving around the Earth experience enough speed and enough gravity, because again, that affects the general relativity part of this, to where they have to actually correct for this. If they didn't, the GPS data would just be wrong that you get on your phone. It would be wrong like pretty quickly and immediately. It would, yeah. So this actually is like important and need to check. And they've done this multiple times. They've sent probes up into space with like very, very, very precise measurements of like, with like gyroscopes and gravity and forces and speeds and stuff. And they actually have determined that yes, this does actually work this way. So yeah, this is super weird, but it's what happens. And we're going to try to do some practice with this. So with that, we'll get the practice in actually. Let's go to the wrap-up question, which is, there it is. What is the Lorentz factor of sound? So if you're moving at the speed of sound, what is your Lorentz factor? So take that as your velocity, plug it into the formula for the Lorentz factor, and see what you get. If you're using like a standard calculator, it probably won't have enough digits to give you an answer. It probably will just eventually just say 0 or 1. So If you want, Wolfram Alpha, again, I think I showed that a while ago, is a good sort of thing to show, to have like a precise calculation. So .com, right? Yep. So this should give you precise enough information if you want to just put it in this way. And again, your number should be very close to 1 if you do it right. So, yeah. All right. So, I'm just going to put it in here just to show you what the answer is. So, let's see. You want 1 divided by the square root of 1 minus want 343 squared divided by 300 million squared. There. I think that should be good. Press enter, see what we get. Make sure, does that look right? Yep, that looks right. And you get that. there's your answer. You get that. And that is, oh boy. Nice discontinuous fraction, by the way. Okay, how many zeros is that? Oh boy. Can I? Not really. Okay. 1, 3, 4, 5. 12 zeros. Six, 5, 3, 6. That's the Lorentz factor of sound. So again, very, very, very close to 1, and you can see how that comes to be. Okay, so your homework questions now. The first one, it's how fast you need to be traveling for your Lorentz factor to be 2. So in this case, you're going to use Lorentz formula but go backwards. So I'm telling you that gamma is 2, solve for velocity. And sort of you can see how that comes into being, that works. And then number 2, so we have Milky Way is moving about 600,000 meters per second towards Andromeda. Milky Way has a length 100,000 light years. Its mass of 100 billion solar masses, and will take about 4 billion years to us to collide. For an outside observer, what is the length and mass of the Milky Way and how long it takes to collide? So, a couple things about this. As you said, notice I see you don't have to convert anything. So because the Lorentz factor is unitless, the gamma itself is unitless, what you're doing when you're changing between the lengths of the times and the masses, it's the same. So for example, I said the mass was solar masses, so that means whatever, if you put in solar masses here, you're going to get solar masses here, okay? And if you put light years in here, you're going to get light years out here, okay? So you don't need to convert, it's just the same unit for whatever it is. And also, you should always check, are the numbers that I'm given the normal numbers, or are they the prime numbers, and therefore which one am I solving for? So in this case, remember, the prime numbers are the ones that are outside of the moving object. So in this case, it's asking, for an outside observer, what are the numbers? So in this case, if I'm standing outside of the Milky Way and, and Andromeda, what are the numbers I see? And these numbers here that we have measured about the Milky Way, well, we are in the Milky Way, so we are moving with it. So because of that, these numbers are indeed the normal numbers, not the prime numbers, and you are solving for the prime numbers. But you have to be careful about that. Sometimes I'm actually giving you the prime numbers, you have to solve for the not prime numbers. So you have to be careful, but this one is kind of the more straightforward example, so you can kind of see how this works. Hopefully with some practice with this will start to make a little bit more sense, but maybe not, because again, this stuff's weird. Let's see. The thing for tomorrow, you will have a worksheet on this kind of stuff to go through and try, which, good luck. Again, it's weird, so hopefully we can kind of work through this and see what you get, but I fully acknowledge this stuff is weird and hard to think about, so don't beat yourself up too much about it if you struggle with this. All right, that's it for me.